Oh, good morning. That's probably better.
Hey, morning.
Good morning. All right, so today we will start the entering the wonderful world of hypothesis testing, which is essentially the foundation of science. You know, anybody can just make any claim, right? You see this all the time on the internet. Your friends make ridiculous claims about anything, like the world is flat, or the acceleration due to gravity is 9.8 meters per second squared. These are all claims, unless they are backed up by scientific rigor. And the hypothesis test is the basis of the scientific method. And so that's why it's an important component of any statistics course. And you know, it's a rite of passage for any scientist or engineer, if you want to call yourself that, because it's the foundation of what you do, right? It's what sets you apart from people that just make stuff up. We're going to learn something that's been used since the Renaissance period in order to advance human knowledge and create all these wonderful things that we have around us, whether it's webcams, microphones, or vaccines and airplanes. The reason these things work is because of the rigor of the scientific process. And we're going to learn the foundation of that in chapter 8. So a hypothesis is really a fancy word for just a claim. And, you know, this could be something like, again, you could say the acceleration due to gravity is, and this is what we're designing lab number 4 to ultimately test, is the acceleration due to gravity is 9.8 meters per second squared. Now we just take this as truth, right? Because we've been told this since we were young, since your first physics course, you were told this is the truth. And why do we believe it? Well, it's because you probably used it in experiments as a constant and got results that could predict, you know, projectile motion, or you're able to figure out the weight of objects using this number. But most people just take things because they saw it on a meme, you know, or they saw it on the internet, and or they read it in a textbook. It's the same thing. I mean, unless you've actually tested it yourself, how do you know this? Right? Maybe you've just been lied to your whole life. Maybe it's something else. And so that's really what lab number 4 is designed to test. So scientific experiments have what's called a null hypothesis, and that's symbolized HO. This is what is called the null hypothesis. And this is the skeptic's point of view. So like, let's say you were to tell me after you conduct your experiment that, you know, let's say your results show that the acceleration due to gravity is actually 9.72. If you told me that, I wouldn't believe you, right? Because it's been shown so many times and the status quo and everybody in the universe seems to believe it's 9.8. And so the null hypothesis is the current understanding or the status quo of what is known about what you're doing. And in this case, in the case of your lab, the null hypothesis would be that gravity is 9.81 meters per second squared. And you've conducted an experiment that shows it's not, right? This is the data from your experiment shows that it is not 9.81, and specifically that it's less than 9.8. And so the alternative hypothesis, which is the one that is it's the one that is backed up by your scientific experiment. Your alternative hypothesis is the experimental data. You're seeing if it's good enough to hold up against the scrutiny of science, right? So this is the sample results. This is where you're building this pendulum to test whether or not the acceleration due to gravity is 9.81 or if it's something else. And that if it is something else is your alternative hypothesis. And there's two ways you can state this. You can say, well, my data it shows that it's 9.72. So my alternative hypothesis is that the actual acceleration due to gravity is less than 9.8. You're not going to be able to prove it is 9.72 because, in fact, your confidence interval says that it's not 9.72. It's somewhere in between, right? You always do a confidence interval first. But what you can say is that it looks like it's lower. It looks like it's lower than 9.8. So I'm going to test that claim. We know it, right? Again, this is the skeptic's guide. The skeptic would say, yeah, right. You made something wrong. Your pendulum sucks, right? Your pendulum is biased. And then you say, no, we conducted it a few times. It looks like we're good. I'm going to try and test to show that where I'm living, maybe the Earth has changed, right? Maybe the Earth is slowing down or speeding up. Or maybe we've lost matter somehow, or maybe we've been lied to our whole lives, and it's not 9.8, it's actually 9.72. This is the claim, and this is the hypothesis test written out in a formal way. For those of you that don't know how babies are made, there's a sperm that comes from the father, and there's an egg. We'll turn this into a little bit of a sexual reproduction class. And from the mother, and the mother always has an X chromosome. And the sperm from the father can either be X, and that would give a genetic female. If the male donates, this was the problem in like England when those kings would kill their queens because they didn't have a son. But really, it was the king's fault because it all comes down to if you have a Y chromosome donated by the sperm. The X and the Y would give a genetic male. Now, according to the law of genetic assortment, this is a 50-50 process. There's a 50% chance, according to the law of what's called independent assortment in genetics. But let's say you're tired of having only boys. Let's say you're with, and so you go in for fertility treatment, and you see that this company advertises that they have a technology, and this is what they quote say on the website. They say with the XSort method, the proportion of girls is greater than 50%. That's the claim that they make, right? They say it's greater than. So that's already the alternative hypothesis. So anytime you see greater than, this is how you know it's going to be your alternative. And so that's what they have here, right? Whenever you see greater than, because why would it be, right? The skeptics guy, like if you told me that we have some sort of fertility treatment, you know, some sort of fertility method that is going to increase my probability of having girls, because let's say again you just want to have a girl for whatever reason. You're tired of all the boys running around your house causing chaos. Like me and my brother, we were rascals. So I'm pretty sure my mom, if this technology existed, would have done this. But the idea is that the fertilization, you know, process, can it be changed? And you know, fertilization treatments, you know, it might allow you to do this gender selection. Do they work? Right? That's the question. So this company claims that they can do greater than 50. And so let's say you try with them and it doesn't work out. Could I sue them? That's the real question here. Let's say I get another boy after going in for this and we have another boy. Could I sue this company? Well, I'll show you in a minute that probably. So why are they making this claim? They're making this claim because they did a scientific, you know, they did a clinical study or some sort of trials where they saw that they actually got 58 girls out of a sample size of 100. And that gives them a sample proportion of 58%. And so the scientists and the statisticians at this company, and this is what you guys will be doing during your capstones, not necessarily this kind of stuff, but you know, the idea is you'll be doing an experiment, you're going to get a proportion of fails or successes, and you want to say this is better than the industry standard. This is a game changer, or whatever it is you're trying to make. You know, before you make that claim, you better be sure that this is not what's called a false positive. Right? We've discussed false positives in chapter 4. Like this looks like, when you first look at this, you say, oh yeah, for sure this is greater than 50%, right? It appears to be greater than 50%. Well, it is greater than 50%. You could probably say it appears to work, right? Our treatment appears to work. Look at this. We have 58% of them are girls. Now the question is this statistically significant? Or is this due to luck? Or just randomization, right? Another word for that. And you say to yourself, let's do a test because I'm a scientist and I took, this is just a claim right now, right? You can just claim, you did a little experiment here, so you can say that you did your science, but you didn't. You've just did this, you did this little, you did part 1 of the experiment, but you haven't finished your scientific process, right? You did your little experiment. Now you have to prove whether or not it's statistically significant or if it's a false positive. Are you sure of your results, in other words? And here's how we do that. So step 1, you set up your hypothesis. Step 2, I guess this should really be here, is what is your experimental data? And from this you can figure out what's called a test score. So just before we go any further, before we actually start our hypothesis test, I just want to tell you that there's 2 methods of doing a hypothesis test that I'll show you in this course. Today, we're going to do what's called a traditional hypothesis test, where we're going to compare what's called a test statistic like a heavyweight match versus what's called a critical score. Or in other words, the confidence at which you need to be right. So there's going to be a throwback to confidence intervals here. So this is what we're going to do today. And then when I see you on Friday, we're going to do what's called a p-value method, which has a lot of advantages as well. We'll do this Friday. So just so you know, if you're going through the practice questions, you'll see them refer to something called a p-value. And so you'll be able to handle that on Friday, after Friday's class. But for now, you'll be able to do what's called critical versus test scores in a traditional hypothesis test. All right, step one, what is your hypothesis? Step two, what was that data exactly? Or you could reverse these, it doesn't really matter. But then step three is you want to figure out the critical score. So the critical score is you want to figure out what your parameters of the test are. You know, what is going to be considered a success? In other words, how confident do we want to be that our results are correct? And usually, again, as we've mentioned before, the standard is really 95% confident. This is the usual standard, or you can say 99, but it's up to you to set that value unless it's specified. In this problem, it's not specified, so you can just take either one of these. Assume 95% or 99 or something traditional. We'll assume 95, then you can just keep increasing it, you know, if it passes the test. But in other words, we want to have a 95% probability that this is not a false positive. And so your critical score, because it's a one-tail, what a one-tail test means, right, if you go back to your hypothesis, right, that one-tail test is that, right, the alternative is that it's greater than 0.5. And so all we're really looking for is our value, basically we're going to test that, is our value of 0.58 far enough away from the null hypothesis or far enough away from what it would be if it didn't work, that it's not going to be from random chance. We need to know if our z-score is going to be where in relative to the critical score. So again, the critical score is setting up some sort of touchdown or some sort of line that we have to cross, and in order to be sure of our results. And so again, if we want to be 95% sure in a one-tail test, then all of the uncertainty is here. And my z-score is going to have to be whatever 0.95 is. So 1.645. All right, so that's the score to beat. So as we're going to see here, if my value is bigger and it falls in here, then we can reject the null hypothesis and say that our data is good. This is what's called the rejection zone, this area here. We call it the rejection zone because it allows us to reject the null hypothesis. In other words, we can say we have enough data to show that we are statistically significantly far enough away from a random fluctuation. Otherwise, you always assume the null hypothesis, right? The skeptic in you as a scientist should be thinking the same thing. Why would I believe your results? Why would I believe that your technology somehow miraculously overcomes the power of God and nature and changes the 50-50, right? The scientist in you should be skeptical of any claim that is not the rational, logical, previously validated truth. I don't know what happened to my camera. I think it's just broken. I think the internet is broken. It must, like, we're always talking about Zoom fatigue. What about the cameras? What about the computers? They must have Zoom fatigue. All right. So what do we do now? Well, we haven't really done anything with our data yet, right? We just set up some sort of parameter that, it's got to be this big or not. So let's actually do what's called the test statistic. So we're going to use this one. Again, there's really just three types of problems. Do you know your standard deviation with a mean? Do you not? Do you know your proportions? Like those are going to, these are the same equations as this, this, and this. People that are not paying attention always make this mistake. You got to be careful. Does the P have a hat or does the P not have a hat? Right, this P is hatless. So is this Q. The only P with a hat is the first one here. And P with a hat, that's the sample proportion. This one is the status quo or the population. So don't make that mistake. Again, it just takes practice. But the score we'll be using is this. So P hat, P, PQN. So what's my P hat? Well, my P hat is the sample data, so 0.58. The P without a hat, so what is the proportion of the population, in other words, without my experiment or without my technology is, well, it's 50-50, according to that law of independent assortment that I was talking about. Right? There's a 50-50 chance that you're going to have a boy or a girl according to genetic theory. Now, of course, it doesn't happen all the time, right? Like sometimes you have a family of like 10 boys. So maybe there's something interesting going on there, but because that's statistically unlikely, but still, as far as we know, this is how genes are divided up into sperms. Okay, so let's keep rolling. 0.58, you just get out your calculator here. And you get 1.6. Okay, so 1.6, okay, that looks very close to 1.64, doesn't it? So the ultimate test, or what we've just accomplished here is this. So if you have, again, draw yourself a little normal distribution, if you want to get extra sympathy from me, because it shows you that you know what you're talking about. The critical score was 1.645. That was the burden of the test. We need to be, if we want to prove that our result of 0.58 is statistically significantly far away from 0.5, then it better be here. Right? That's the rejection zone. Think of it like a touchdown. You got to get into this touchdown area. Now, we did not. 1.6 is over here. Right? Our actual test score, I usually abbreviate it ZT. It doesn't beat it, right? 1.6 is over here. And so it means that this could be just a little fluctuation, right? We need this in order to prove it's not a false positive. This looks like a false positive. And so what you say is your answer is because the test score is less than the critical score, The terms that you'll see in the slides and in the textbook, it's a little formal, but it's the proper way of saying it. You say we fail to reject the null hypothesis. In other words, the burden of proof is always on the experimenter to show that your results are statistically significant. We fail to reject the status quo. We fail to reject the null hypothesis. Now that sounds really formal, right? That is the formal claim, right? That is the formal way of saying it. But what I want you to do on your third quiz, coming up next week or the week after, whenever it is, next time you write a test, make sure after you write this, tell me something in English, right? Tell me something that is not like techno geek stuff, because that's what you're really going to have to do when you talk to your boss or something like that, or you make a press release to the newspapers, is you want something that actually makes sense, right? This is really nerdy. Because the test score is less than the critical score, we fail to reject the null hypothesis. It's like, what the hell does that mean? What you really want to say is, it appears that the XSort technology works, but we would need to test more, but is not, like, because it does appear that it does work, because you get a 58%, right? It appears that XSort technology works, but is not statistically significant, or is not statistically valid. Or you can say, we can't rule out that it was just luck. Or another way you can say it is, more testing is needed to validate the results. All this kind of good stuff. Something like that. But just something that, again, that you would say to a person that does not speak statistics, right? Again, you, me, and 500 other engineers that are studying at SAIT understand the importance of numbers and the importance of using the proper words when describing things. But when you get out into the real world, right, you have to be able to say something like this: we need to test more, or let's keep optimizing the process to get better, so we can be sure that we just didn't get lucky. Something like that. Especially when you're doing your lab report, right? You'll notice that in lab number 4, there's a section for 250 word comments. Make sure you give me something like, our pendulum, whatever. Say something interesting. I'm not going to tell you what to say. I think you're at the point now where you should feel comfortable creating a document that is interesting, and try to have some fun with it, right? I mean, if you don't like this kind of stuff, then you're in the wrong field, right? I'm pretty sure that, I think I mentioned this before, Excel, if you're lucky, Excel is going to be a major component of your life. Those are good jobs if you're there working on Excel projects. And, try and, again, it's not fun when you first start doing it, or if you don't know how things work, it's definitely not fun. But once you start understanding the logic behind some of these processes, you'll find that it becomes more entertaining as well. So you have to wait a while.